All right, now all of these linear algebra problems may be said to have what is called a geometric interpretation. That is, in terms of the subspaces. So we looked at the solutions in terms of their point solution. It involved a normal equation and so forth. But what's going on in the subspaces back behind all of this? We know that there are subspaces. There's a range of A. B is not in the range of A. We talked about the null space of A. So we have these different things going on. So if we consider the underlying vector space and subspaces, we can see the geometry of the solution. In particular, the projection theorem applies, and we thus seek a projector for the appropriate subspace. For the overdetermined problem, we're letting our subspace be the range of A. For the underdetermined problem, we're letting M be the kernel of A, or the null space of A. And so in each case, we're looking for a projector. So given B and M, then we desire to minimize the norm error. That is, the error which is a function of M minus B, where M is in the subspace. So if M, for example, is in the range of A, then if M is then M can be thought of as being A times X for some value of X. The minimizer to this minimization problem is going to be orthogonal to M. The error is orthogonal to M. So we have seen that already. M is this, so M star is such that the error is orthogonal to M. And as a result, there is a projector that maps the subspace, the entire vector space, onto M. And the minimizing solution then, M star, is equal to that projector times the B. Okay? This is the thing that we're looking at. So this is the projection theorem, and we can actually use it for both the overdetermined and the underdetermined problems, the way we've defined them. So again, given A and B, these dimensions, we desire to minimize this error. In this case, our subspace is the range of A, and so instead of just using M here, we're actually explicitly saying M is equal to A times X. Okay, minus B. Again, we have the two cases, overdetermined, underdetermined. In each case, there is a projector. So if B is, if for the overdetermined case, B is not in the range of A, the projection theorem says that if M we choose as the range of A, then the error is orthogonal to that subspace. And so in this case, for any M which is equal to AX, the error of X star of the minimizer satisfies this relationship. 0 is equal to A delta. So this is the normal equation. Okay, this is the normal equation that comes out. Okay, so in the normal equation, we have that this must be satisfied. Again, with the solution map, this must be satisfied. Now, if I look at what this equation is, if I multiply through by A adjoint, that's going to give me A adjoint A times B is equal to A adjoint. Okay, and I can go through and show that this equation being equal to 0 actually implies these two equations. AB adjoint is equal to AB, and A is equal to ABA. And so we can go through and prove that this one equation is equivalent to these two equations. Okay, this equation shows that AB is self-adjoint. This equation is the equation for what's called a generalized inverse. That is, B is a generalized inverse of A. Okay, and that's why it works as a solution map. It is because it's a generalized inverse. It's not a pseudo-inverse. It's a generalized inverse. The projection for this problem, E, is equal to AB. And so we notice that by this condition, it is self-adjoint. To show that it is in fact a projection, we take E squared, which is E times E. That's equal to AB times AB. But ABA is equal to A. And so this is just equal to E. We'll later talk, when we talk about the pseudo-inverse, we'll show that E can also be written as a pseudo-inverse. So this is the overdetermined problem. notice that the overdetermined problem tells us a lot, but it doesn't tell us how to compute B. Okay? It doesn't tell us how to... Neither of these two equations tells us specifically how to compute B. Okay, so that's significant. By way of example, given this matrix, we can go through and show that this solution map, that this B is a solution map. That is, it satisfies this, and it satisfies it regardless of the values of A and B. So this shows that the solution map is not unique. All right, so it turns out that if our matrix A satisfies this condition, if A adjoint A has non-zero determinant, when we take A adjoint A, that will give us a square matrix. That square matrix, if it has non-zero determinant, then we can show that we have a unique minimizer. That is, x star is equal to A adjoint A, quantity inverse, times A adjoint. That times B. And our solution map is given by this expression. Okay? So, in this case, we have a minimizer. In fact, this quantity now is actually, in this problem, is actually the pseudo-inverse of B. We'll talk about the pseudo-inverse in a little bit. Again, we have the projector, which is AB, which is all of this stuff. And again, we can go through and show that it is self-adjoint. So we can show that for this B, that this B satisfies those two equations. A is equal to ABA, and the quantity AB is self-adjoint. And so for this overdetermined problem, what if A adjoint A has zero determinant? Well, it turns out there is still a projector E. It's just that E is not given explicitly by this formula. It actually is given by this formula, but B is not this, okay? Because we can't take the inverse of it. Okay, but we can still have a projector. Okay, and so in this case, A times X adjoint is equal to E times B. So it turns out that this condition can occur whenever the matrix is said to be not full rank. So in the event that a matrix is not full rank, it turns out we can go through and show, using elementary row and column operations in linear algebra, that there exist non-singular matrices L and R such that L is equal to, or L, this matrix times R, where little r is the rank of the matrix. Okay, and we can go through and show that an R is a, so L and R are non-singular. This is singular. I can also show that there are matrices F and G, where F is this matrix and G is this product. So F in general is tall and thin, G is short and fat. All right, and each of these matrices F and G are full rank. That is, the rank of this matrix is R. The rank of this matrix is R. So, turns out that any matrix can be factorized this way. Now, if your matrix, for example, is A, for example, is, let's say it's already full rank, then, for example, F would be A and G would be an identity. Or G is equal to A and F is an identity. You can always factor it that way. So we can define this projector. So for a given matrix A, which is equal to F times G, we can get this projector. E is equal to, notice it's only a function of F. Okay, I can go through and show that this matrix is self-adjoint, this product, and it is consistent with the solution map B. That is, E is equal to AB. And since it's self-adjoint, and since, so ABA is equal to E times A, right? That's E times A. But E is all of this stuff. So notice that when I multiply this by A is F times G, I get F adjoint F multiplied by F adjoint F quantity inverse. So that all that goes away, leaving F G, which is A. So we can show that in fact E defined this way gives a B that satisfies the normal equations. So if A times X star is equal to EB, that is if FG times X star is equal to E times B, notice that F is multiplying the front side of both of these equations, so I can drop the F, which is full rank, and just get G times X star is equal to this quantity. So we started off with an overdetermined problem, but this problem now, in general, this is short and fat. This problem in general is an underdetermined problem. Okay, and so we can actually work with the underdetermined problem by working with the null space of G in all of this. So we may have an infinite number of solutions. The smallest of them is given by the pseudo-inverse. So I've talked a little bit about the pseudo-inverse. I haven't talked directly about it. So in the next video section, we'll talk about the pseudo-inverse.